Okay, first question. This is for Doug. For companies that are new to DFAM, designed for additive manufacturing, where do they start, and what's the low-hanging fruit?
Yeah, so I think the big thing is, and I think Peter touched on this, is really have that application that really you can take advantage of the design for additive manufacturing and make that part that makes sense to make in additive. Not every part's going to make sense, and many won't. But if you have that application that either has that part consolidation, like you mentioned earlier, which is quite often probably the lowest hanging fruit from if you're doing traditional design, you've been designing parts for a long time, and if you can take advantage by taking an assembly, putting it together in one part, reducing either that assembly cost or maybe some quality control, that kind of thing, to combine those parts all in one. That kind of is probably the low-hanging fruit, but you can get into a lot of other added benefits very quickly if you make that decision that your part is correct for additive manufacturing. Then you can start taking advantage of a lot of the other tools that are in our toolbox to drive more value into your part or product at the end of the day. And I think that's the key, is we want additive manufacturing to add value to the product, and use those special features and geometries and textures that we can do in additive manufacturing that you can't do in maybe a more traditional manufacturing, such as injection molding or something like that. So really taking advantage of those special aspects.
Yeah, thanks, Doug. So one thing that Olaf Deagle stresses. Olaf is one of our associate consultants and lead. Olaf. He says time and again that it's got to add value, and if it doesn't add value, then it's just not worth pursuing. Peter, a question for you. What is your favorite DFAM application?
That is always one of the trickiest questions to answer, because we just see so many, right? And it's really, really unique, because you'll see something that is amazing in terms of it's reduced the drag of for example, a race car, and it's helped them to achieve a lot better speeds, and you think, okay, that's amazing. But then, for example, we see something like conformal cooling, where all of a sudden they've increased their shot time by 30% or 40%, and they're taking traditional manufacturing into the future by using additive manufacturing, and I really love that. It's not, additive isn't just about creating parts; it's also about creating things that manufacture other things, right? So, to be honest, I don't have a single one. One of the things that I really do always love seeing is part consolidation. So anything that's got more than 10 parts down to one, I'm always incredibly happy to see.
I couldn't agree more. John, do you have a favorite?
Well, one of my favorites is this. So this is BMW's first metal 3D printed part that they publicized a couple years ago. You might say it's not the kind of thing that's gonna make billions, because it's a roof bracket in one of their high-end roadsters, but it's a beautiful example of the design freedom you get by AM, using advanced software, and also the hard constraints of manufacturing. Because if you look up this story, and it's one we really emphasize in our courses, you learn how they designed this to essentially be support material free, and that was key to be a strong business case. And they claim it was cost competitive against die casting for the quantities, a few tens of thousands of this vehicle. So it's one of the most memorable to me, because it's a great mashup of the opportunity of additive and supply chain flexibility in printed metal parts, and this has a real serial number on it. It's a real part, and also how you have to bring manufacturing constraints into the equation if you want to have a good use case.
And it needs to be cost competitive. Not always, but most of the time. If it's not, it's very difficult to sell within your organization. If it's 50% more or 2x or 10x more, you still may be able to justify it if it really stands out in terms of performance and part consolidation and so forth, but very difficult to sell. John, so how is additive manufacturing changed, or will it change the roles of designers, engineers, and others in product development?
Great question. I think ultimately it's blurring the lines between those roles, right? Because traditionally we teach or we aspire to the ideal that design to manufacturing is a linear process. Now we all know that's not true because you have to know about manufacturing to be a good designer. But when you think additively, everything is matched and mixed together, and that's both a challenge and a huge opportunity. So you have these hybrid individuals who do design and integrate manufacturing with design. You also have in some of the leading organizations adopting AM, new modes of teamwork, and get material scientists, researchers together with design engineers, with product engineers, with supply chain folks, and try to rethink the whole operation. And for instance, we had a workshop about a year ago at MIT, and we talked about how do you recast traditional roles into an additive organization, and you see things like metallurgists becoming data science savvy, or quality engineers. It's not the quality engineer goes away. The quality engineer's role is elevated earlier stage and has to think about new modes of data-driven qualification, for instance. So overall, it's just I think a blurring and recasting of traditional roles and injecting new knowledge into those roles.
Yeah, thanks, John. I couldn't agree more. Thanks to the people attending for submitting questions, and as you can tell, if you haven't already, that you can vote, in the most popular questions for us bubble to the top based on the number of votes. So I'm going to start diving into one or two of those. The one so far that has received the most votes is around materials. Should DFAN be focused on certain materials, not only how to design for certain technology, but also for material and application? Doug, do you want to, or any one of you want to dive into it?
I can start. I think, I don't know that it has to be focused on, but I think there's certain materials that can take advantage of it a little faster than other materials. And John's example of the metal bracket, I think is great because with metals you can really take advantage of that weight savings and the topology optimization to get the strength where you need it and where you want it, and really reduce the amount of material in the part. So I think that's where metals really shine with DFAM. I think in the polymer side, the elastomers, I think, have a lot of opportunity to really take advantage of DFAM in the fact that you really offer variable stiffness throughout the part by changing geometry. And just a simple example, you have this part that is very squishy over here and very stiff over here, just by changing geometry with the same material. This is in Lubrizol stain, but TPU. So I think depending on what your application is, I think materials are definitely going to drive the adaptation of DFAM quicker in certain spaces.
Doug, you mentioned elastomers. Can you name a specific example of practical application at AVID that where elastomers are used additively?
Yeah, absolutely. So yeah, we're printing with the thermoplastic urethane, the stain M95 TPU, and we use that for a lot of different applications. We're seeing protective parts for AR VR goggles, right? That's something that we do a lot of, or different components for damping in industrial applications. And there's just a lot of opportunities in those scenarios to take advantage of that variable stiffness that you can apply. We're seeing lots of interest in the footwear space as well. I think there's a lot of opportunity. And then prosthetics and orthotics is another space where we're seeing lots of interest with the elastomeric materials.
Peter, I sent you.
Yeah, no, I think that it's really interesting. And one of the things that we always find that, you might have the same problem, and when you're looking at 5 or 6 different materials, you'll see completely different answers of what the best solution looks like. So that's one of the things that we've been doing quite heavily, a lot of research on in terms of what material is going to be good for what problem. And one of the things in our generative design technology is you can do multi-material, multi-solution simulations. And then you can actually just compare them. You can say, well, this is the best alternative if we do decide to go with titanium. this is what we can do if we want to go with Inconel. This is what we can do if we actually figure out there's a way to do it in, you know, ABS. If we can go into plastics, that's going to help to save the weight even further. So, you know, there's a lot of different solutions that are available for the exact same problem. And I think that going into it with the mindset that this is the only material that can solve that problem. Of course, there are situations where that is the case, due to, you know, fire retardant kind of things, or, you know, certain other criteria that you need to be meeting. It's definitely one of those things that if you don't lock yourself into, we need to use this material, you can actually find some quite unique and some better solutions for the problem. So I think that taking away as many of the constraints from the problem really helps to find the best solution.
Yeah, couldn't agree more. I like this question from Gabe, and it ranks as one of the top. What is a DFAM advantage that is not widely recognized within the industry itself? In other words, what's the best kept secret around DFAM? John?
Yeah, actually, I don't think there are any big secrets, and that's a good thing. You know, we as an industry have a strong and growing awareness of what the value propositions are. But I'd say, you know, there's probably an unexpected wow in your organization, in your day-to-day, if you really dive deep and you bring additive, you know, to the people in your organization. You know, you know, in addition to things like the design use case from BMW, I love the use cases on the shop floor where you have a splint to help a worker who's, you know, does a job that's, you know, really difficult, you know, hour after hour, or, you know, fixtures on the production line as well. And also, maybe my last point here is, I think the DFAM at the higher level of the organization is maybe hard to capture. We recognize, we say supply chain impact, we say organizational impact, but how you value that flexibility and agility is a really hard thing to model and articulate, and also sometimes is a little bit of a tug against the traditional ways that, you know.
Uh-oh.
Oh, we lost him.
We lost John. I'm sure he'll be back.
Terry, I'd love
Doug?
to jump in on that one because
Sure.
I'm pretty
Please.
passionate about this. I think there's a very simple DFAM component that kind of gets overlooked sometimes, and it's really surface textures. And it's something that with the right tools, you can apply to many parts, and it can do a lot of things to help drive that part to a product. The dirty little secret in additive manufacturing is that, and lots of people can print a part, but to make a product, you need lots of post-processing and finishing and make it look like that finished product, right? So to do that, we have a great example here where we're working with a company that makes electric vehicles, and they convert electric vehicles. And they needed a component to hold all of their electronics, but they needed it to look like the dash. It needed to match the dash of the vehicle that it was going into. And so, you know, applying a leather texture of some sort to a 3D printed nylon part can do a lot of things for you, in that it can hide, what I always say is it hides some of the sins of 3D printing. All 3D printing has layers. It all has layer lines on some level, but you can mask a lot of that by applying a texture to hide it. And it reduces the amount of post-processing that you might have to do. So then you might just bead blast part, apply a coating to it for the UV protection and color, and you're good to go. So I think a lot of that upfront work that you can do, that's a little easier even if with the right tools, can add a lot of value to the part. Again, going back to the value thing.
Yeah. Peter, do you have something to add?
Yeah, no, I think that it's really interesting. You know, when we're talking about like the cheeky hidden secret of DFAM, I think that one of the biggest kind of secrets or the misinterpretations of what DFAM is that everyone thinks it's really hard. I mean, there is, of course, a lot of things that go into it, and you need to understand quite a lot about the process. But if you take, you know, a couple of days to actually have a look at what is going into it, what is required for the design work, what the machines are requiring, it's not that tricky. You know, there's a lot of great tools out there at the moment that really allow you to take full advantage of the 3D printing technology. And it's just a matter of thinking about what we need from this part and kind of, you know, just being almost silly and saying, why do we need this part? why do we need that? Why? And just consistently asking yourself why, because quite a lot of the time, especially if it's a bracket, right? You see so many different applications where it's like we're improving a bracket, but you know, if we can look at trying to consolidate that, if we can kind of look at, okay, well, what can we customize that? What if we can, you know, instead of having a part optimized, do we really need it to have those strength properties? You know, looking at, you know, potentially having modular systems. And I think that one of the things that we see a lot more of coming up, especially in automotive, is that the specific number of parts that is determined to be mass production has come down significantly over the last few years. You know, so previously, you know, when you're looking at a company like Toyota or something, they've got, you know, 50,000 is the minimum criteria for it to be mass production, whereas now they're starting to look at, you know, 25,000. And the numbers are slowly coming down as the product development process is speeding up. And I think that that's an area that we really see additive starting to play more of a crucial role in, is that, you know, mass production is slowly becoming a very very changing landscape. And I think that that's an area that we're going to see quite a lot of advantage coming out in the future.
Yes, absolutely. Is design holding back the adoption of additive manufacturing for production applications? And if so, what are some of the reasons? And I'm going to try to start this discussion by saying that time and again, I've witnessed companies in industry, you know, waking up, a light bulb comes on, they say, we got to look at using additive for the production of this or that. And then they start peeling away the layers and understand, to really make this worthwhile, not in all cases, but in many and arguably most cases, you really have to design for additives such as part consolidation and some of the other things that have already been discussed. So then they understand, we need to train our people or somehow figure out or educate people so that they can design, and so then they start heading down that road. That can be expensive and time consuming when you're pulling engineers off projects, and especially in today when people are running very, very lean, depending upon the industry. The bottom line is that it becomes very expensive just to determine whether or not you can apply it, you know, economically and otherwise. You know, apply the project or the product to additive manufacturing, or apply AM to that particular job. And so it becomes to the point where companies kind of get to a point where they throw up their hands and walk away. And it's not until, you know, they become less competitive due to their competitors do they, you know, pick it back up. Can one of you maybe talk to that? Have you seen that? What are some of the other maybe obstacles holding back AEM, design-related obstacles?
So I think that one of the things that I always come across is that a lot of these companies, especially in very large manufacturing organizations such as automotive, is that even though it might be, for example, the engine, you'll have 4 different siloed organizations designing specific critical parts within that engine. So when you're looking at doing part consolidation, you need to have a huge amount of organizational cross collaboration. And I think that that is almost just as more difficult than DFAM itself. So navigating the political landscape in some of these larger organizations that have a huge amount of cross-functional, that have very little cross-functional engagement with other teams, that's incredibly tricky.
I think, I imagine this is something that John probably will be able to touch on a lot, especially in the education world. But, you know, I've been a design engineer, mechanical engineer for 25 years. And, you know, at some point during that time, I had to retrain myself on some level on how I'm looking at parts, how I'm looking at products, and how I'm going to design those parts and products. Because it's using some of those same skill sets in a different way. And really learning how can I use this term a lot, cheat with the design compared to how I used to do it. If I used to design an injection molded part and I had to have very uniform walls and bosses had to be designed just right, all of that. Now, if I'm going to consolidate that part and make it an additive part to add that value, I can also now take advantage of other things that I couldn't have done before in the injection molded part. I can sheet, I can have different wall thicknesses, I can have undercuts and lattice structures and all that stuff that wasn't even an option and now is. So I think that re-education, relearning, being maybe almost a little more creative in how we design products, I think allows us to take more advantage of it when it's the right part.
So John, what are the challenges in teaching DFAM that you've encountered, and what are some best practices?
Yeah, I think Doug's comment is right on. I think we've learned that it helps to emphasize the process fundamentals. There's many processes out there, but they can be distilled down to a discrete set of fundamentals. The design tools, the access to software, at least know how the software works and how to talk to those using it. And then the practical side, the domain applications, and that's the creative ideas, but also just the knowledge that you have from what you do every day, and putting those together for us really leads to this hybrid understanding of design for additive. And also I'll say I've been really pleasantly surprised by how engineers embrace the business side and the cost modeling and the understanding of the economics. And once you have the design possibilities, opportunities, right, you want to abandon like a little bit of, oh, I'm worried this is going to cost too much or so on, but then you have to get to being able to go back and forth between the two. And one thing I wanted to say that to me is a big limitation, or where we need to get, is being able to have more confidence about what additive can do at the early stages of our design process. What I mean is knowing confidently what the material properties will be. And also one of the barriers to industrialization is quality at scale, right? We know there's a lot of great possibilities, but if you decompose a lot of the scaled applications, they're in the real high value markets, or they're where the organization just had money and people and time and patience to fight it through the through the process, and as the technology grows, even if we froze all the materials and machine development and software development, now we just focused on like quality systems and building that capacity at scale would go a long way. And to me, that's one of the biggest barriers to being able to follow through and impart more confidence at the early importantly open-ended stage.
John, you mentioned cost modeling. Do you have tools at MIT to do that?
Yeah, I mean, we've developed just some spreadsheets, and I don't consider them especially kind of breakthrough, but been very useful to our students and the participants from industry in our courses. And I sort of sometimes they're like, well, this is really basic, but you see when an organization says this is a great spreadsheet, we're going to take it over and use it internally. I'm like, wait a minute, are you sure it's good enough? But it's very good to see that. And also in some of our research, we're trying to connect the physical process limits to the cost model, right? Like you can buy a metal 3D printer and know that it has a certain laser spot size and a certain build area and a certain build rate. But when you get into it, that the performance depends on the geometry you're making and the process parameters. So we're trying to look forward to, you could say customization of equipment or optimization of equipment for particular use cases by connecting the equipment design and parameter selection to, the cost model itself.
Sorry, Terry. I just think that the cost model is extremely important, and I'm glad you touched on that, because the economics around additive is so important. It's got to be competitive. It's got to be the right use case for it. And we find ourselves going back to our spreadsheets and our cost models quite often, revamping them, really understanding how can we be most efficient to make parts cost effective. How can we nest them the best to make as many as possible in one build, and all of that. I think the economics are going to drive applications like they do in every other area of manufacturing. Additive's no different. So I think that's a really important place to focus on and use the DFAM tools to drive costs down and functionality up.
And I mean, just touching on that, so I think that it's a really interesting topic, and one of the things that we need to think about also is that it's not just how do we reduce the cost of doing it in additive, it's what would the cost of doing something very similar to this be in 3-axis milling, right? Or what's going to be the same price of doing this in a different material using 5-axis? So one of the things that we've been quite focused on with the generative design technology is that with all of the different results across all the different materials, we also have a rough estimation of price of building it with that manufacturing technology in that material, in the full lineup of all of the different designs that come out of the software. So not only do you have an idea of what the mass compared to the the volume of material consumption will be, but you also have an idea of what the production cost would look like. And you can also put in the number of parts that are going to be created in that production lot. So it really helps to actually take into account some of those more financial side and some of those pricing equations during the initial design stages.
We have a question from Philippos. This is having to do with post-processing, which is absolutely important when it comes to cost and other factors too. Considering the constant development of post-processing methods and technologies, how do you see DFAM changing in order to take advantage or take into consideration this stage of manufacturing a part? So I guess the bottom line is, how do you factor in post-processing when designing for additive?
I think it's
taking out
critical.
just taking out any constraint. That's great, right? One less constraint, if you have less requirement for supports, that gives you a huge amount more ability to go crazy with the designs, right? It is kind of interesting because during the conversation, when we were talking about all of the students that go through John's course, it's almost we train them to forget everything that they've learned until now because they've been so focused on traditional manufacturing. But it's really interesting when we're kind of developing software tools or we're developing algorithms, they're creating very, very advanced, very complex designs with additive, and we actually need to kind of take them and very much strongly guide them in how to create designs for more traditional and more constrained projects. So adding the constraints is actually more difficult from the algorithm and from the software side, but from the human side, it's actually more difficult to train to develop for complexity. So it's a really unique way for us to start looking at how we bring in the unique capabilities of what the engineers can do and what the unique capabilities of the software that's coming out onto the market can do. So it's kind of a very unique kind of, they're kind of crossing over and we find a nice equilibrium somewhere in the middle. But yeah, it's been very interesting to see how the algorithms are calculating parts compared to the way that humans are calculating parts at the moment. So it's becoming very interesting.
Doug?
I think considering the post-processing is really important because that's one of the largest labor components of printing parts and making products, and so that becomes one of the most costly components of making parts. So if you can have a part that you're printing and if you design it differently, either so it's more robust or it has channels that you can get the powder out if it's powder bed fusion, and you can automatically blast it versus manual blast it, right? Now you've saved hours of time and lots of money. So as the engineer, and this really falls back onto the designer then, and the engineer to be thinking as they're designing that part, not only do I want to consolidate all these components into one, I want to add these cool lattice structures, but can I get the material out or the support structure or the powder out of that lattice structure easily? And how can I make sure that that flows through the process so I'm not adding costs down on the production floor when it's time to manufacture this product? So thinking about that early on, and that's probably where we see some of the most iteration of the design is how do I make it so that it can be more cost effectively manufactured, and post-processing is probably the biggest component of that.
This is a design by Olaf Diegel. It's a small still to make alcohol, though in the state of Colorado it's illegal to do that, so we use it to purify water. Other things are legal in the state of Colorado, but we cannot use this to make alcohol. So I just wanted to mention that. But the point is that this little still would have many, many support structures. This is made in aluminum, and you would have to remove those, metal against metal, a lot of work. And what Olaf did with this design is what would otherwise be support material, he turned into features, such as you can see here. And these elliptical shaped holes And inside, you can see the winding tubes. Normally, there'd be a support material between those tubes. Well, he built a wall there. So in the end, 0 support structures to build this fairly complex piece. The only, of course, you need some material to anchor the part to the build plate, but other than cutting, removing this from the build plate, it's pretty much finished. Maybe some surface finish, but light surface finishing. And so you can design to reduce dramatically and even eliminate support material, not on all parts, but in some parts. So that's something that one needs to consider.
Yeah, if I want to jump in there, Terry, sorry. It's a great example to me of how, design for additive is ultimately like a human machine or human software collaboration. Like the tools from Autodesk and others are getting better and better, but they're learning from, the human creativity of examples like that. How can you you get around the limitations, change the shape of features, considering post-processing. Another great one is like, if you're going to drill out or ream out holes anyway, make them diamond shaped so they're self-supporting. And you see that in some of the really compelling examples. And I also think we're still just in the early stages of those software tools that combine the human intuition with the computational power.
Yeah, absolutely, John. Speaking of software tools, this next question is around it. DFAM is largely about putting software to work. Not entirely, but largely. And we've seen some amazing tools that are developed in the recent past, and many companies have adopted them and really doing amazing things with them. What are some of the biggest obstacles to developing next generation software solutions for DFAM? So if you can look into the future, and I'm guessing Peter might have an opinion on this.
I mean, I guess that as we're adding a lot more complexity to the situation, we have companies that come to us and say, we want to do optimization for lightweighting. We also want to do optimization for CFD. We want to do, thermal dynamic simulations and having parts generated based on all of these inputs, but we can't use cloud. And it's like, well, unless you have a supercomputer, there's not really too many machines that are going to be able to calculate all of these very complex equations while also then developing a geometry that meets the requirements. So one of the things that we do have issues around is the adoption of cloud. And at the moment, that is definitely going to be one of the things that's going to be a real enabler. We see a lot of companies that start to use it. One of our greatest allies, I think, in our journey to achieving success in additive is potentially going to be Amazon, right? The guys that are going out and selling Amazon Web Services, they've just signed contracts with Toyota, they've just signed contracts with the US Army. There's a huge amount of stuff that's going on. And the more that they're able to use these more advanced tools, the more they're going to be able to use advanced design technologies, the more they're going to be able to use more advanced simulation capabilities without having that massive infrastructure investment that would be required to bring in that computing power. So to be honest, I think that at the moment, the very low amount of companies that are able to use cloud is definitely hindering the growth of the industry.
Doug, John, what's your favorite software tool?
Oh gosh, favorite software tool. I think it's the combination of tools. Sorry, Peter, but we've been a SolidWorks company for a long time. Lots of great tools out there. So we, that's our main CAD tool. But then we move into some specialty tools to drive the DFAM, right? So N-topology, we have some very powerful users of that N-topology in our design team. And we're playing with the general lattice guys and doing some really cool stuff with what they're doing. So it's a combination of all those tools and having the right tool for the right job at the end of the day.
John, do you have a favorite or two?
Yeah, I can't say I have a favorite. What's been most powerful to us to engage large numbers of people are just the tools that are cloud accessible. You can use them in the browser, easily install them, and maybe it's not the most sophisticated, FEA solver for getting to the final stage of design, but lets people collaborate, easily learn the techniques, and then you might carry that forward, or you might transition to a more, as you could say, sophisticated tool, once you finish our course, for instance. And that's CAD, that's generative, and other cases. And also great to experiment and be aware of all of them. For instance, if one wants to play with build preparation, you can download Cura, which drives Ultimaker and a lot of FFF printers, or Preform from Formlabs, among others, and you can play with those. And it's not like doing really advanced support generation for metals, but it has a lot of the same principles. So I would emphasize the accessibility of software as being key to learning, and then figuring out what's the best tool for your exact mission and specifications you need to focus on.
Yeah, in the old days, you used to have to buy the software before you could try it. Now you can try it and then later decide. So for the most part, Peter, what's your favorite non-Autodesk software?
It's always a tricky one. I mean, one of the ones that we always have really great connection with is the guys at Anthropology. It's a team that I've got a lot of great connections with. Half of the team is ex Autodesk guys as well, so I'm always having good chats with them about some of the really new technologies that they're working on and the ways that they're helping their customers to achieve. And it works very well. We have a lot of customers that have been doing great work in generative, taking those parts out of generative, putting it into topology optimization, and then doing very complex conformal latticing with those parts. So it's not that one software is there to completely control the industry. It's more that each different tool has very unique capabilities, and the ability for an engineer to kind of take them and work within each of the tools' best capabilities is definitely going to help them to achieve more. So that's any of the guys at Anthropology will probably be more than happy to give a bit of a demo. I think they've got a table here as well.
Okay, we have maybe time for one very quick question. It's I see it just turned over to 7:15 in the morning here in Colorado, Mountain Time Zone. Quite early yet. One word, your favorite 3D printer.
Well, for us, it's HP Multijet Fusion. That's our bread and butter. It's where we make thousands of parts every day. So,
John?
Impossible to say. I'll say that it's the printer that comes next, the next new one.
Yeah. This, by the way, ranked 18 people voted in favor of this. Martin wrote this question. So, Peter, do you have a favorite?
I mean, to be honest, I don't have a specific printer that I love more than the others. I love all the different technologies because each of them have really amazing applications. But I mean, at the moment, I'm being quite interested in quite a lot of the DED capabilities. We've just been seeing quite a lot of very large industrial manufacturers moving to that. So that's an area that, to be honest, I'm a little bit immature in. I don't have a huge amount of exposure to it, so I'm enjoying the learning that it's offering me. So that's an area that I have been getting a bit more involved with. So I would say at the moment, DED is my most challenging technology, which is also keeping me engaged very strongly. So.
Yeah, well, it's a little bit like the question I've been asked multiple times over the years. Over 30 years, companies would ask individuals at organizations, what's the best 3D printer out there? And I'll turn that around. I'll say, what's the best vehicle out there? If you're wanting to impress a spouse or a girlfriend, boyfriend, whatever, versus haul a bunch of school children, lumber, it depends. I mean, you really need to select the right vehicle for the job, and then the same is true with 3D printing. So with that, I'd like to thank our three panelists. Thank you very, very much, Doug, for getting up so early. John's fairly early and on the East Coast as well. Peter, thanks for staying up late. And I'll turn this over back over to 3D Native. So thank you very much for your time and expertise today.
Thank you, Terry.
Thanks,
Terry. Thanks, everyone.